Condition variables, waiting and signaling in monitor implementations. In this presentation, we will explore condition variables, which are fundamental synchronization primitives used in monitor implementations to manage thread coordination. What are condition variables? Condition variables are synchronization primitives that enable threads to wait until a particular condition occurs. They work in conjunction with mutexes to provide a mechanism for threads to coordinate their execution. The purposes of condition variables are: they allow threads to wait for a condition to become true. They enable threads to signal other threads when conditions change. They provide a way to coordinate access to shared resources, and condition variables are an essential component in monitor implementations. Core operations on condition variables. Let's explore the core operations associated with condition variables, focusing on how threads interact with these primitives to achieve synchronization. The first operation is wait. Wait operation atomically releases the mutex and suspends the thread until signaled. Typical usage pattern is while not condition convar.wait mutex. When a thread wakes up, it automatically reacquires the mutex. The second operation is signal operations. Signal, also known as notify1, wakes up one thread waiting on the condition variable. Broadcast, also known as notify all, wakes up all threads waiting on the condition variable. Typical usage pattern is condition equals true convar.signal to wake up one waiter. Condition variables in monitor implementation. Condition variables are a fundamental component of monitors, providing a way for threads to wait for specific conditions while temporarily releasing exclusive access to the monitor. Inside the monitor, there is mutual exclusion with a single mutex lock, ensuring only one thread is active at a time, providing automatic acquisition and protection of shared data. In addition to the mutex, there are condition variables with multiple wait queues, where threads block on specific conditions, using signal or broadcast to wake them up, enabling effective coordination. Wait operation in detail. Let's delve deeper into the wait operation, examining the step-by-step process a thread undergoes when it invokes this operation on a condition variable. When a thread calls wait on a condition variable, these are the steps involved. Step 1 atomically releases the mutex lock. Step 2, the thread is placed in the condition's wait queue. Step 3, the thread is blocked until signaled. Step 4, when signaled, thread reacquires the mutex. Step 5, execution continues after the wait call. Typical usage pattern is mutex.lock. Check condition in a loop for spurious wake-ups. While not condition, convar.wait mutex, which releases mutex and blocks, and then reacquires mutex when woken. Process when condition is true, process shared resource. Then mutex.unlock. Always use a while loop instead of if statement to handle spurious wake-ups. Signal operation in detail. Let's dive deeper into the signal operation, exploring the sequence of events that occur when a thread invokes this operation on a condition variable. When a thread calls signal or notify1, these are the steps involved. Step 1, if threads are waiting on the condition variable, one thread is selected to be awakened. Step 2, the selected thread is moved from the wait queue to the ready queue. Step 3, the awakened thread will attempt to reacquire the mutex. Step 4, if no threads are waiting, the signal has no effect. The signaling thread continues to hold the mutex unless it explicitly releases it. Typical usage pattern is mutex.lock. Modify shared state. Shared resource equals new value, condition equals true. Signal that condition has changed, convar.signal or notify1. Then mutex.unlock. Signal versus broadcast. Signal wakes up exactly one waiting thread. Broadcast wakes up all waiting threads. Signaling strategies in monitors. When implementing monitors with condition variables, different signaling strategies can be employed, each with its own advantages and disadvantages. The first strategy is signal and continue. How it works is, the signaling thread continues execution after the signal operation, while the awakened thread must wait for the signaler to release the mutex. The advantages are signaler can complete its critical section. It is more efficient in some scenarios and simpler implementation. The disadvantages are awakened thread must wait longer and may cause priority inversion. The second strategy is signal and wait. How it works is the signaling thread immediately releases the mutex and waits, allowing the awakened thread to proceed immediately. The advantages are awakened thread runs immediately, it is better for priority-based scheduling, and reduces context switching in some cases. The disadvantages are it is more complex implementation, signaler must reacquire mutex later, and may cause unnecessary context switches. Producer-consumer example with condition variables. Let's examine a classic producer-consumer scenario that demonstrates how condition variables are used to synchronize access to a shared buffer. The producer function is as follows. While true, produce item equals produce item function. Enter critical section, mutex.lock. Wait if buffer is full. While count equals buffer size not full. Wait mutex. Add item to buffer in equals item, in equals in plus 1 modulus buffer size, count plus plus. Signal consumer, not empty. Signal. Exit critical section, mutex.unlock. The consumer function is as follows. While true, enter critical section mutex.lock. Wait if buffer is empty. While count equals 0 not empty. Wait mutex. Remove item from buffer, item equals buffer out equals out plus 1 modulus buffer size, count minus minus. Signal producer not full. Signal. Exit critical section, mutex.unlock. Consume item item. Two condition variables are used, not empty and not full. Best practices and common pitfalls. While condition variables offer powerful synchronization capabilities, it's essential to follow best practices and avoid common pitfalls to ensure correct and efficient concurrent programs. Some of the best practices are always use while loops instead of if statements when checking conditions. Signal immediately after changing the condition state. Use broadcasts when multiple threads might be waiting for the same condition. Keep critical sections as short as possible. Use separate condition variables for distinct conditions. Some of the common pitfalls are using if instead of while for condition checks, which is vulnerable to spurious wake-ups. Forgetting to lock or unlock the mutex. Signaling before changing the condition state. Using the wrong condition variable for signaling. Creating deadlocks by incorrect lock ordering. Key takeaway: condition variables provide a powerful mechanism for thread coordination, but require careful implementation to avoid synchronization bugs. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.